So, today I will demonstrate Frank-Hertz experiment. This is historically important experiment. So, actually in 1913 Bohr proposed the model of atomic structure where discrete energy levels for accommodation of electrons were postulated. So, in atom there are energy levels, that energy levels are discrete energy levels. So, that was the Bohr postulated, that the electrons can rotate certain energy levels, certain levels, and when it will rotate it will not radiate any, it will not emit any radiation. So, based on these postulates, basically Bohr given the atomic structures in atoms, how electrons are arranged. So, that basically this main point was the discreteness of energy levels. Actually, so you can think of like this, the positive charge concentrated at a particular region. So, that is that's the nucleus. So, around the nucleus there are energy levels, okay, circular orbits or cells. So, electrons can only stay in these energy levels, it cannot stay in other energy with other energy, okay. So, that energy levels also we can draw with these horizontal lines. So, in this case I have this n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, so n equal to 1 also there, and he derived the energy of these levels. So, for nth level, so energy is En equal to minus 1 by 4 pi epsilon 0 square m e to the power 4, m is the mass of the electron and E is the charge of the electron, divided by 2 h square h cross square. H cross is basically h by 2 pi, h is Planck constant and n is the basically principal quantum number. So, there is the orbit number or cell number. So, this was the quantitative expression for energy of the hydrogen like atom. Hydrogen like atom means the outermost cell will have one electron, and this theory is extended for other hydrogen like atom like sodium, potassium, etc. Later on also it is extended, it is basically corrected to use for multi-electron system like helium and this lithium, then beryllium, so for other atoms, okay. So, helium, neon, argon, etc., this is another group of atoms, it's we tell that is the inert gas. So, there basically all cells are closed, means these orbits have maximum capacity of accommodating electrons. So, when this maximum number of electrons are there in that cell or in the orbits, then we tell it is a closed orbit or shell, it cannot accommodate more electrons. Okay. So, helium is a 2 number of electrons, neon 10 number of electrons. So, they basically their outermost shell are closed. So, that is why we tell them that the inert gas, it does not react with other atoms, because it has no interest, because this outer shell are full, and it is stable, it cannot want to give electron to other, it cannot, so these atoms are not interested to share their electrons with others, either do not want to accept or do not want to give. Okay, so that is why it is we tell the it is the inert gas. Okay. So, anyway, so that in 1913, so that was the proposal of Bohr, that we tell the Bohr model, and their main important assumption was that the energy are quantized. It is the energy, electron cannot take any energy, it can take only particular energy. So, that is the discreteness of energy levels. So, that assumption was experimentally verified by Frank-Hertz immediately next year. So, that is why it is this Frank-Hertz experiment which demonstrated the discreteness of energy level. So, that is why it is a historically very important experiment. So, that experiment today I will demonstrate in our optics laboratory. So, in 1914, J. Frank and G. Hertz performed experiment to demonstrate the quantum nature of atomic states or energy levels. Okay. So, this the experimental setup is very simple. So, this is a tube, glass tube. So, in this tube there is a cathode which will emit electron. So, this cathode is heated with heater. Okay, I have drawn here filament. Now, electron will be emitted. Now, in this tube, this helium gas is used. Helium gas is used. So, when these electrons will move, it will collide with the mercury atoms. Mercury atoms are available in gaseous form in this tube, and this electron will reach to the anode. Okay. Positive, cathode is generally negative terminal and anode is positive terminal. So, this electron will reach to the anode, and we will get some current because of the flow of this electron through this anode. So, we will get current, that is called the anode current. So, that anode current, why we are getting? No, from the cathode electrons are emitted, and that electrons through this tube will come and reach to the anode, and that will go to that electrons, it is grounded here. So, some positive voltage is given, it is grounded, it is grounded basically. Okay. So, it is similar to negative voltage. Okay, it is grounded. So, it is we will get current in that is called anode current in this circuit. Now, question is that electrons emitted from the cathode, so it will have some energy, thermal energy. So, with that energy it cannot travel this length if we do not give some external energy. So that's why, so this here we are showing this is a grid, this is the grid. Grid means it's a one wire, but having the holes, okay, so that this will act as a, so here we are giving basically positive voltage with respect to the cathode. So electrons will see the potential difference between the cathode and this grid, that potential, that is the positive potential. So electron will be accelerated with energy EV, E, and this potential difference V, EV. So in this case it is U1. So EU1 with this potential difference, or EV1, that with this energy, it will come to the grid and it will pass through the holes of the grid. Okay, that's why it is called grid basically. So it's small holes are there, and here actually here we have given some negative voltage, small negative voltage. Okay, so when this accelerating voltage or energy of this electron, that is basically kinetic energy E1, when it will be greater than the energy, that the potential U2. Okay, so when it will be able to overcome this retarded potential, here basically negative potential means retarded potential, then it will reach here. So for this experiment what we do, we give a small retarded potential, so that with this thermal energy whatever the electron emitted from here, so with this small energy it will not be able to reach in the anode. Initially it will not be able to reach to the anode. Okay, so that's why we will not get any anode current. Now what we will do, we will increase this E1 voltage. That means I am increasing the energy, kinetic energy of this electron, that is basically charge U1. Okay, so then that electron will overcome this retarded potential and it will reach to the anode. Okay, so I will increase the U1 and more electron will reach to the anode, and I will get more and more current. I will, like here I have done it, I will get more and more current. So at this U1 potential, so suddenly we see the drop of the current. And then again we are continuing the increasing of the U1. Then we are continuing the increasing of U1, and then again current is increasing. So instead of monotonous increasing of the current, it is giving us like step kind of increment of the current. Okay, so that means at certain U1 voltage, it suddenly this current dropped. Okay, so question is, why this sudden drop of the current, anode current is coming. The sudden drop of the anode current means at that voltage, this suddenly electrons, sufficient number of electrons are not reaching to the anode. Okay, so and that is happening at particular voltage, not all voltage, it is a particular voltage. Okay, so this reason behind this is that the mercury atoms are there. So in mercury atom, So it's the atom, it's the atom. So electrons while moving through this gas, so it will collide with this atom. So there will be scattering. So that is basically elastic scattering. So this electron will not lose any energy. So that's why it's called elastic scattering. But at certain voltage we are seeing that this anode current is decreasing, means electrons is losing energy, somehow it is losing energy and it has no sufficient energy to reach to the anode. Okay. So most of the electron will not reach to the anode at a particular voltage. So this is happening because the inelastic scattering of the electrons at this particular voltage. What is that? So it may happen that at this particular, at this energy, at this voltage, these mercury atoms, it's due to the collision of the electrons, so electrons, the energy of the electrons are absorbed by the mercury atoms. Okay, and this absorption, that is basically inelastic scattering. So this absorption of the energy by mercury atoms, it is happening only at certain voltage, at certain energies. So this is basically it may happen if these mercury atoms have discrete energy levels. So when the energy of the electrons are equal to the energy difference of the energy levels of the mercury atom, so that energy will be absorbed by the mercury atom, and the electron from lower energy level to the higher energy level, it will jump. Okay. So if so, then there are certain energy levels in the atoms, in the mercury atoms, and there are energy difference between these energy levels, and when the energy of the electrons are matching with the energy of the difference of the energy levels of the mercury, so that time it is absorbed and electron will lose the energy, its kinetic energy, and it is unable to reach to the anode. That is why this suddenly current is dropped. Okay. And this is happening for a energy difference between close energy level, between the nearest two energy levels, and then second one is happening, it is happening between the say, this is if this one is for first and second energy level, so next one will be first and third energy level, then next one will be first and fourth energy levels. Okay. So it will be able to jump to the higher and higher and higher energy levels of mercury atom when the energy of the electrons are matching with that energy energy difference of the energy levels of the mercury. Okay. So this was observed, this type of pattern of the anode current as a function of accelerating voltage. Okay, this kind of pattern was seen. Okay, and this pattern is basically clearly demonstrating the discreteness of the energy levels of atoms. Okay. So now this experiment I will demonstrate in our laboratory. So here you can see the experimental setup. So here you can see that tube, that glass tube, where that mercury gas is there, mercury are there. Now in this tube basically we have cathode, we have cathode. So here you can see, so this diagram is drawn here, I think, yes, diagram is drawn here. So this is the glass tube, whatever I showed here, this is the glass tube, okay. So this is the cathode, and UH here whatever written, that is basically heater current, that filament, heater current is given to this filament, and then that cathode, it's connected with the negative voltage U1, you see U1 negative voltage, okay. And then we have grid here. In my diagram I have showed you the one grid, but here there are two grid, okay. So this is one grid and this is another grid, but both are connected with this voltage U1, okay. So so it's same, one can use one grid, one can use two grid, there is no problem, but same voltage is given U1. So this is the accelerating voltage basically, and this is the anode, and this anode is grounded, okay. Or here it is the U2 voltage. So this is the deaccelerated voltage is given to the anode U2, this negative voltage with respect to the U1 grid voltage, it is negative, okay. So so it is the basically retarded voltage for the electron, and U1 is the accelerated voltage for the electron. Retarded voltage between the grid and anode, why it is given, I explained that with small energy electron will not be able to reach to the anode, okay. So we will not get current. So so here electrical connection, I think I can show you. So this is the power supply basically, from here we are taking this connection, this giving to the electrode, okay. So it's here UH is retained, so heater current, heater voltage is given, power is given. So here it is written U1, okay. So here it is basically U2, okay. So this from this power supply, this is here is given, and you know mercury is basically liquid, okay. So to make it gaseous form, we have to heat it. So there is an option to heat this this gas, this mercury, to make it gaseous form. So here we can see there is a one thermocouple is there to measure the temperature, okay. So now here you see in this power supply here 177, you are seeing here this temperature, this is basically you can see T actual. So these are in degree centigrade, okay. So this is the temperature, constant temperature for the mercury gas, to keep mercury in gaseous form. So this temperature, constant temperature is kept, and here you can see this, I can change here, it is a IA, means it will show here anode current, okay, it is now 0, and here it is showing this UH means heater current is given, this is the UH 1.2 volt, and if I continue, this is U1 voltage, U1. So here this is the upper limit we have put here. So maximum 60 volt we can apply. So that is the restriction given by the company, that we should not apply more than 60 volt accelerating voltage. And then if I change this U2, it is here you see 2.0. So that is the deaccelerated voltage. So we kept it constant, we will not change U2. So some small deaccelerated voltage is given between grid and the and the anode, okay, between the grid and the anode, and then this is U3. There are some other options also there, but we do not need. So, here what we will do, so this experiment we can do in manual mode as well as automatic mode. So, now what I will do, here I will yes, I think I will choose PC mode. No, I will choose PC mode. So, in PC mode means, so here we have interfacing with the PC, here we have interfacing with the PC, okay, we have interfacing with the PC. So, you can, I will just, so there is a software, this is given by the company. So, you forget automation of the instrument. So, here manually I can change the, what I have to do, the, what is the experiment? Experiment is basically I will change U1 and I will change U1 and I will note down the current IA, okay. So, manually you can do, and then we will take the data and we will plot the data in a graph, okay. So, then you should get what is the type of pattern you should get, that I have shown you, okay. So, instead of doing this, noting down the data and plotting in graph paper, so here this screen I am using, okay. So, that will be displayed, that graph will be displayed directly here, okay. So, in PC mode, I think in PC mode I will show you. So, in PC mode means I am using this one, this screen only, okay. So, what I will do here, I will select this experiment, Frank-Hertz experiment, I will select this Frank-Hertz experiment. So, here option is that automatic and manual control. So, I want to do manually, means I will change the U1 and note down the IA, and then I will plot. So, that I am not noting down, okay. So, this PC will help me, that just I will change the U1 and corresponding current. So, that will be that U1 versus IA, that will be plotted directly on the screen. So, if I take this one, so manual I have chosen. So, this the showing this, it will give me current IA, and I will change the voltage. Here I will make it 0. Okay. U1 voltage initially I am putting 0, and U2 I am keeping, this is following errors, okay, it is there is no voltage U1, okay. So, I think fine. So, it is showing me data that your temperature is 175, your heater voltage is 6.3 and U2 is 2 volt, fine, and U1 is 0 volt. So, I will start experiment. So, U1 is 0, current is here, it is a 0 here. Then I will change the U1 0.1, 0.2, 0.3. Here you can see it is the current, it is the plotted, corresponding current is plotted. Okay, I am changing 1, 1.1, 1.2. So, quickly I am changing because initially I need some higher voltage. So, now it is 5 volt. At 5 volt you can see still IA is 0. current is 0, anode current is 0, then I am going first, I am changing U1, it is around 8, yes 8.1, I am changing, you see still it is 0, current is 0, scale is automatically changed. Now slightly current is coming, but not stable. Now current is increasing, you see I am continuously changing, current is increasing, and then yes current is, you see the change of current IA with the U1 voltage, it is like this, So I am using the, so here I am changing the, using the mouse to change the U1, and you see the current is changing like this with the U1 voltage. Now U1 voltage is 34, then 35, then 36, 37, 38, 39, okay, 39, okay. So I will snap 45, 46, 7, 48. So I will go up to 50. Okay, it's the 50. You see, U1 voltage is 50, and then current is changing like this. So whatever the pattern I have shown, which we are expecting, if the mercury atom have the discrete energy level, so this kind of variation of the anode current is expected, and that is because of the setup of the experiment. There we have applied retarded potential U2, and we have applied the accelerating potential U1. Okay, so exactly the same type of pattern we are getting on the screen. So from here basically one can find out this. So where current is dropping, so that voltage corresponding that U1, so that is basically matching with the energy level, with the energy level, energy levels of the mercury atoms. Okay, then the next one, so that way you are getting different number of peaks. So this manually one can do this experiment. So this is the demonstration that this pattern of the anode current is nothing but the signature of the discrete energy levels of the atom. Okay, so that's the historical experiment, and it confirms the postulates of the Bohr. It confirms the atomic structure proposed by the Bohr. Okay, so just here also one can take this experiment. I will stop this experiment. And here basically, so whatever we have taken data, so that's one is here. So this is U1. This scale is U1 by V means in volt, and this is IA anode current by Na means nanoampere, in nanoampere. Okay, so this also one can do this experiment automatically in automatic mode. So computer software itself, it will vary the U1 in step, and it will note down the current IA, and it will plot here. So that let me show you, but that is not important, that is not the important for the experiment, that is nothing but the sophistication of the experiment. Okay. So without this screen also you can do the experiment manually, you have to note down, but since we have done this interfacing, so that is why we are using it. Okay. So actually you do not need this computer or interface. So automatic mode if I choose, so then continue, you can see I start experiment, you can see I am not doing anything, just it will it is just changing the U1 and plotting the current variation of anode current variation as a function of U1 at a particular temperature, of course we have chosen. So this the experiment is done. Okay. So you are getting the same whatever manually I got this in automatic mode also you got the same thing, and if you do note down the data, change here itself and note down the data and plot in a graph, you will get this. And from this peak, actually we take this position here, okay, dropping position where it is dropping. So if you note down and you can try to match, you can try to match with the energy levels of the mercury. So I think that I am not going to do, but just to give this one hints. So mercury there is a 80 is the atomic number. So if you so here this Abba principle, okay, how electrons are arranged, electrons are arranged in the energy level, so that you know. So here I have just 80 electrons I put like this. So here you can see this outermost level is 6s, and here these 2 electrons are there. So this mercury structure, electronic structure is similar to the inert gas, you know. Helium, you remember, it has 2 electrons and it is 1s2. Okay. Neon, it has 1s2, 2s2, 2p6. Okay. 10 electron. Okay. So its structure is like this. So that's why it's not inert gas, but it's behave like that. It does not react with the other ambient atoms. Okay. So and also it is easy to get in pure form, liquid form, pure form, and it does not react with, it's like a inert gas atomic electronic structure. Okay. And you can make it easily after applying heat at 175, as I showed, you can make it gas form. Okay. So that's why we have used helium. So not we have used, so it was used that time by Frank-Hertz. So that is the reason why helium was used. Okay. So now the 6th level, okay, outermost energy level 6th level. So these 6s, now we can plot 6 other, okay, 6s, then you have 4f, 5d, after that 4f, I think, then 4f is full, 5d is full, 6p. So 6s, then 6p and 6p, then 7s, okay, then 7s, then 5f, then 5f, okay. So this kind of energy levels are there. Okay. So here 2 electrons are there. If you hit, so this electron, depending on this energy, kinetic energy of the electrons, so it will jump here, it will absorb that energy, electron energy, it will jump here. then if energy, so it's the first, because of this you are getting this, say this first drop, and then you are increasing the energy, energy is sufficient, it's the difference is like this, okay. So then it will, so again you are changing the U1, it's the increasing, when it will be, energy will be equal to this energy difference between these two levels, so then it will be absorbed and it will jump here, it will jump here, okay. So then again it will, so this way okay. So that is the reason of this energy drop, and which is the signature of this discreteness of the energy levels of the atoms, okay. So this fantastic experiment, simple experiment, historically very important experiment, okay. And from this value actually one can exactly, it is difficult, some correction we need, but approximately you can find out this structure of the energy levels. So this, what are the separation of the energy levels above the 6s, so that one can find out, okay. So I think I will stop here. Thank you for your attention.